fact, there is no non-constant polynomial f of n with integral coefficients which take on just prime values for integral n. That is, f of any integer. There is no function f of n such that f of any integer is always our prime. Well, let's prove this. Let's start off with a polynomial, non-constant polynomial with integral coefficients. So f of n is, say, a sub k n to the k plus a sub k minus 1 n to the k minus 1 all the way down to a sub 1k plus a sub 0, where it is a true case degree polynomial. That means a sub k is not 0. Okay. Suppose f of n0 is prime. That is, f of n0 is ak n0 to the k plus a sub k minus 1 n0 to the k minus 1 all the way down to a1k a1 n to the 0 a1 times n sub 0 plus a1 is equal to p, a prime. Now, to show that this polynomial f of n can always put out a prime, let's consider this. Let us consider f sub n0 plus t prime. T is some integer. So we're looking at infinitely many inputs, one for each integer t, and p is that value. Okay, so f of n sub 0 plus t sub p, this is going to be a sub k times n sub 0 plus tp to the k plus a sub k minus 1 times n0 plus tp to the k minus 1 all the way down to a sub 1 times n0 tp to the 1 plus a sub 0. Okay. Now, when you FOIL this out, you're going to get, and that, whatever it FOILs out to, it gets multiplied by a sub k. You will get n0 to the k plus a sub k minus 1. When you FOIL this out, one of the terms will be n0 to the k minus 1. That's going to come from the binomial theorem, all the way down to a1 times n0. That one's more obvious. Plus a0. Let's bracket that off. Plus the other terms. The other terms are all going to have a factor of p. All the other terms other than this term is going to have a factor of p. The other term is going to have a factor of p. And the a sub 0 I already dealt with. And it's not just going to have p, it's going to have also our polynomial in the variable t. I mean, for example, n0 plus tp cubed. It's going to be n0 cubed plus 3 times n0 squared t squared p squared plus 3n0. That should just be TP, please. So this will be t squared p squared plus t cubed p cubed. But the p is just the constant. You have n0 cubed plus 3p n0 times t plus 3n0 p squared times t squared plus this coefficient times t cubed. I've already dealt with the term that just has n sub 0. There it is. There it is. There it is. Okay? I already dealt with that. So let's just ignore that. Every other term, it has a p, at least one p, which I factored out, and after you pull out one of the p's, to make that p squared, it is now a polynomial in terms of t. And that's what I said. Okay, just a few more lines. This is p plus p times q of t. This is p times 1 plus q of t. Now, by assumption, f of n0 plus tp must be a prime. Well, you can multiply a prime times another. Well, let me back up a little bit. We know that p divides f sub n0 plus tp, because this is a multiple of p. That's the multiple. Now, since p is prime, and this by assumption, f of n0 plus tp is a prime. This implies that f of n0 plus tp is that same p. That is, not only do I get outputs, well, ignore that. This is p for all t in the integers. Okay, but there's one problem here. A case degree polynomial can't have the same output for more than k inputs. In other words, if you have x squared plus 2, a quadratic, you can only obtain a value, the same value, 2 times. I mean, this value we only obtain 1 time, and this value no times. Now, if you have a cubic equation, you can only attain a particular value up to 3 times. 1, 2, 3. Okay, this value right here, we got 2 times. 1, 2. And since this goes down forever and it goes up forever, we're never going to have 0 times. But the bottom line is, if you're a 3rd degree equation, you can take on the same value more than 3 times. This is a fourth degree equation. It can take on this height 4 times. It can take on this height, this is a horizontal line, 2 times. Okay, it can take on this value no times. Now just for the record, a fourth degree polynomial can look just like that. And it can take on this value 2 times, never more than 4. Just like a cubic equation, like y equals x cubed, it only takes on a value 1 time, but never more than 3. Okay, but we have a slight problem here. This here represents infinitely many inputs, and each one of them have p as an output. Infinitely many inputs is greater than k inputs. Okay, and that's a contradiction. We're getting too many p's. We're getting f of more than k inputs with the output p, and that can't be. So f of n equaling only primes for integer inputs can happen. Can happen. And that's what we wanted to prove. There's a really nice proof there. I didn't come up with it, but it's a nice argument. See you guys in the next video. Subscribe to my channel, click the like button, leave comments, and watch and learn.